So in the last video we looked at the empirical formula and we described it as a chemical formula which represents the smallest whole number ratio of atoms in a particular compound. And we're going to carry on looking at this, except in this video we'll be focusing on a specific type of calculation where we can basically work out the empirical formula of a particular compound given information on the masses of each element within that compound. And that might sound a little bit confusing, so I'll explain it using this first example. In this question, we are asked what the empirical formula of a compound is, which is made up of 69.6% oxygen and 30.4% nitrogen by mass. So we have this compound. We know that the only two elements are nitrogen and oxygen. Out of the total mass of this compound, 69.6% of that mass is the oxygen, and the other 30.4% is the nitrogen. So with this information, how do we determine the empirical formula of the compound? Because at the moment, all we really know is that it's made up of these two elements, nitrogen and oxygen. So the first thing we need to do is find the relative atomic masses of the elements that we're dealing with. In this case, nitrogen and oxygen. This is very easy. All we need to do is look at the periodic table. Nitrogen has a relative atomic mass of 14, and oxygen has a relative atomic mass of 16. And the reason we need these numbers is because in the next step, we divide the percentage by mass values that we're given here for each element by their relative atomic masses. So for nitrogen, we divide 30.4, which is the percentage by mass, by the relative atomic mass, which is 14. And we get this number here. We do the same for oxygen. 69.6 divided by 16, and we get this number here. I've rounded up these values to 2 decimal places just to make it a bit easier, and we write these values as a ratio, as it says in the step. So now, the reason for doing this step is to find the relative amount of each element. So that basically means that for every 2.17 atoms of nitrogen, we have 4.35 atoms of oxygen in the compound. Now, of course, we wouldn't write these numbers as part of the chemical formula. It's a ratio, so we can simplify them. And that's exactly what we do in the last step. The last step tells us to divide both of these values by the smallest one. So for nitrogen, we divide 2.17 by itself. 2.17 is the smallest number out of these two. So we get 1 for that. For oxygen, 4.35 divided by 2.17 will give us a number very close to 2. The real number, if you put this into your calculator, is actually 2.0046, but we can round it up to 2. So this is the smallest whole number ratio, or the simplest whole number ratio of the elements that we have in this compound. We have 1 nitrogen for every 2 oxygens. This means that the empirical formula in this case is NO2. So that's how we do it. The calculation essentially remains the same if we're using the masses in grams of each element instead of their percentage composition by mass like we've done here. And you will see an example where we do just that in a minute. So on this next page, I've just included the basic steps for a question like this. Questions like this are quite common and will probably come up on the exam, so I would recommend writing these steps down. Now the next part of this video looks at a kind of combination of what we've covered so far with a basic lab experiment. And from this experiment you would be able to work out the empirical formula of a compound, and the compound we're looking at specifically is magnesium oxide. And I'm going to walk through the steps we would take to produce it and tell you exactly why each step is done. So we have something called a crucible, which is a hollow container that we use generally to heat compounds to very high temperatures. We have a gauze mat and a tripod. The tripod is used to suspend the crucible and allow us to heat it from below using a Bunsen burner. And the goal here is to form magnesium oxide from magnesium and to determine the empirical formula of magnesium oxide. So what we do to start off is we heat the crucible to a very high temperature to burn off and basically evaporate any substances inside. Anything which may contribute to the mass which isn't the crucible or its lid has to be removed. We then leave it to cool down before weighing the crucible with the lid on and recording the mass that we get. And you'll see exactly why it is that we do this in step 3. So step 3, what we do is add a piece of magnesium ribbon to the crucible and then weigh the crucible with the magnesium inside. So we have a second value for mass here that we get in step 3. What we do is take away the first value obtained in step 2. That's our first value, from the mass obtained in step 3. Now the first value accounts for just the crucible and the lid. The second value that we get accounts for the crucible, the lid, and the magnesium. So if we took number 1 away from number 2, we know that the difference between these two numbers is the mass of magnesium that we use, basically. So that's why we do this, to get the mass of magnesium. That's the goal of step 3. Step 4, we heat the crucible with the magnesium inside, and we place the lid on the crucible while we're heating it, and this prevents any solid inside from escaping, but at the same time we allow a gap. And this enables oxygen to enter the crucible. And that part is very important, and I will refer back to it later on. Step 5, we heat the crucible with the magnesium inside for 10 more minutes, or until the solid has turned white. When the solid turns white, we then assume that all the magnesium has reacted, and we have nothing but magnesium oxide in the crucible. The final step, step 6, we allow the crucible to cool down, and we then reweigh it using the exact same method that we did for step 3. But we'll have a third number this time. So we're essentially weighing, in step 6, we're weighing the crucible, the lid, and the solid inside. We obtain a value for this, and then we subtract the value that we obtained in step 2 for just the crucible and the lid, and we can assume that the difference between these two values is the mass of magnesium that we have at the end of the experiment. So I'm going to go a bit further here and actually apply this experiment to a calculation, referring back to the steps on this page as I do so. Now we're given a calculation question. We are told that 1.45 grams of magnesium was heated in a crucible so that it completely reacts to form magnesium oxide. We are also told that the mass of magnesium oxide formed was 2.42 grams, and then we're asked to calculate the empirical formula. So the first value, the mass of the magnesium, which is this value, is obtained through step 3 of the experiment. Steps 4 and 5, obviously we heat the crucible to a point where we can assume that the reaction is finished, and that no more of it can take place. And this second value that we get, 2.42 grams, which is obtained through step 6, is the mass of magnesium oxide that we have at the end of the experiment. Now this mass that we get at the end, 2.42 grams, for magnesium oxide is higher than the starting mass of magnesium. So what has happened in between? Why has the mass increased? Well, if we actually take a look at step 4, what we do while we're heating the magnesium is we keep the lid on the crucible, but we leave a small gap which allows oxygen to enter the crucible. Now let's be clear. Magnesium oxide, as the name suggests, is made up of only two elements, magnesium and oxygen. We start with just magnesium, but while heating it, the oxygen we allow into the crucible reacts and combines with the magnesium to form a new substance, magnesium oxide. That is why the mass increases. Now we're asked to calculate its empirical formula. However, in the previous question, which we did on the first page, the numbers for mass were actually just given to you. For this question, you actually do have to do a bit of extra work in order to get all the numbers you need. But we'll begin the calculation anyway. So first thing we need to do is obtain the relative atomic masses of the elements involved. This is 24 for magnesium and 16 for oxygen. The next step is to divide, in this case, the mass in grams of each element by its atomic mass that we've already found. This is the extra bit of work I was talking about. And we'll start with magnesium when we do this. The mass we're given for magnesium is 1.45 grams. Because we place the lid over the crucible when we heat it, we can assume quite safely that the magnesium remains inside the crucible throughout heating, and therefore its mass stays the same. So the value of mass for magnesium is 1.45 grams. For oxygen, what I said just now was that the increase in mass between the two values was a result of oxygen reacting and combining with the magnesium. So the extra mass that we get at the end of the experiment is from oxygen. And so simply what we do is subtract the first value from the second one. So 2.42 minus 1.45 will give us a value in grams of 0.97. This is the mass of oxygen in our magnesium oxide. We now have everything we need. For magnesium, we divide 1.45, that's 1.42, 1.45 by 24. And for oxygen, we divide 0.97 by 16. For both of these, we get two numbers which are very close to each other. You can do this on a calculator if you want to get the exact numbers, but both of them are very close to 0.06. We write this as a ratio. And of course, if we divide both of these numbers by the smallest one, where the only option is 0.06, we'll get a ratio, a 1-to-1 ratio for magnesium and oxygen atoms. And so the empirical formula for magnesium oxide is simply MgO. This also happens to be the molecular formula as well.